Okay, so now we're going to do chapter 1, section 5, which talks about exponential functions. So we talked about linear, we talked about quadratic, we talked about cubic. Here's another one, exponential. Okay? Now what's interesting about exponential, it's used in a lot of word problems like continuous compound interest, population growth, radioactive decay, and many other applications. Okay? So a basic exponential would be like 2 raised to the x. So let's put that in our calculator. Okay? So we go to our calculator. We're going to type in, go to y equals 2 raised above the division x. Now for this exponential, I'm going to give you the window that works well with exponentials. The window is going to be negative 10 to 10 counting by ones, 0 to 10 counting by ones. That will give us a good graph of our exponential. Okay? So instead of having 2x or x squared or x cubed, it's a number raised to the variable. Bless you. A number raised to the variable. And what does exponential look like? A nice curve going upwards. Nice curve going upwards. Okay? So, the general form of it is f of x equals a base, a number raised to x, where the base is greater than 0, and the base cannot be 1. Defines an exponential function for a different constant being called a base. The domain is a set of all reals. The range is all positive reals. Okay? So if I was going to make a table for this, and I plugged in -4, 2 raised to the -4 is 1 over 16, so forth and so on. 2 raised to the 4 is positive 16, 4 over 16. You can see that it grows quickly, and we say grows exponentially. So if I put the dots on a graph, and I connected those dots, that would be the graph of an exponential. Just hit the calculator. Okay? Now, what would happen if I put 2 raised not to the x, but to the negative x? So let's do that to the calculator. So in y2, y equals, in y2, instead of saying 2 raised to the x, let's put 2 raised to the negative x. And to make sure we know which one's which, move all the way to the left of the y2, push enter, and let's make that bold. Let's make that bold. Hit graph, and let's see what happens when it's a negative x and not an x. There's the original, and there's the other one. And it looks like a reflection. And a reflection about what? Is it a reflection over the x, or is it a reflection over the y? Over the y. Okay? And the data will look like that. It's going the other way. And if you graphed it, it will look like that. Okay? So some basic properties. These graphs contain the point 0, 1, since b to the 0 is 1 for any permissible base b. The graphs are continuous curves with no holes or jumps. The x-axis is a horizontal asymptote. If b is greater than 1, then b raised to the x increases as x increases. If b is between 0 and 1, then b to the x decreases as x increases. Okay? You already hopefully did Appendix A, so you remember your exponent rules. But if I had a to the x times a to the y, that's a to the x plus y. If I had a to the raised to the x divided by a to the y, that's the same as a x minus y. If I had a to the x raised to the y, that's the same thing as a x times y. And if I had ab raised to the x, the same thing as a to the x times b to the x. And the same thing as a over b raised to the x, same thing as a to the x, b to the x. Exponent rules, things hopefully you remember. Appendix A working with all those. A to the x equals a to the y if and only if x equals y. X cannot equal to 0. If a to the x equals b to the x if and only if a to b. And be careful, -2 squared equals 2 squared. It does not contradict the property 3 of 0. Okay, you may have seen e before on your calculator. So if you look on the calculator, you have a 10 raised to the x and an e raised to the x on the left side to the left of 7 and to the left of 4. Okay, you have to hit second log and second ln. Those are buttons we're going to practice in a little bit, and they're often really important ones that show up. Okay? The base e is an irrational number, and like pi, it cannot be represented exactly by any finite decimal or fraction. The base e can be approximated by evaluating the expression 1 plus 1 over x raised to the x for some sufficiently large values of x. So if I plug in numbers, you're going to notice that it gets really, really close to larger number 2.71828 and keeps going. So it's a number that goes on forever. It's used often. Instead of writing that decimal that goes forever, we just write. So an example would be 2.7182818284592. Y equals e to the x and y equals e to the negative x. Before, domain, range. If we graph both, that's what it will look like. So let's go to our calculators. In y1, let's graph e to the x. And in y2, let's graph e to the negative x. Let's make sure we know where those numbers are and we're comfortable with them, with those keys. So we go to the calculator. In y1, let's do e second ln. Second ln x, clear, second ln negative x. And we can keep the same windows last time. You notice it looks very similar. Last time we did 2 raised to the x, e to the x is 2.78, so they look very similar. Okay? Just getting comfortable. Functions in the form c times e to the kt, where c and k are constant and the independent t represents time, are often used for model population growth and radioactive decay. When t equals 0, then y equals c. Constant c represents the initial population. K is the growth rate. Let's do an example. Okay? Cholera, a very fun topic, is an intestinal disease. It is caused by a cholera bacterium that multiplies exponentially. The number of bacteria grows continuously as relative growth rate 1.386. That n equals n to the 0 e to the 1.386t, where n is the number of bacteria present after t hours, and n is the number of bacteria present at the start. So bottom line, it's growing exponentially. There's your e. How is it growing? 1.386 t for time. N to the 0 starting. So I haven't given you that yet. So if I told you, if there are 25 bacteria at the start, how many bacteria will be present in 0.8 hours? So I'm going to show you 2 ways we're going to practice our calculator. Number 1, let's just type it in. So let's go to our calculator, go to the home screen by hitting second mode, and let's just practice the button. So the initial is 25, E second ln, and that's 1.386 times, the first question is 0.8 hours. So times 0.8, hit enter, let's make sure we know where the button is and we're typing it correctly. Did everybody get 75.768? Okay, I'm gonna show you a quick shortcut. I'm lazy, I don't want to type that in again. So hit second enter. If you hit second enter, what does it do? Copy and paste. Change the 0.8 to 2.5, which is our next question. Hit enter. You should get 799.41. Okay? That's one way. Let me show you something else your calculator can do. We've done this before. Go to y equals. Get rid of y1, get rid of y2. In y1, put 25 e to the 1.386, but put x in. Put x in. And we did this last time. We used the table feature, but I'm going to make sure our calculators are set up again. After you type that in, hit second window. Second window. We set this up last time. It should say Ask Auto. If you're not bringing your calculator every week or if you're swapping it out, if yours says Auto, change it to ask auto. Then go to the table feature, second graph, type in 0.8, type in 2.5. So it's a quick way to type in as many numbers as you want using the table feature. Now, if you're not able to type in numbers, that means when you hit second window, yours still says auto. You gotta change it to ask auto. So when you go to the table, you can type in 0.8 and 2.5. Did that not work for anybody? Check your calculator. Not work? Worked? Didn't work? Worked? Second graph to get to the table. And then you type it in. Are you able to type it in? Yeah. We good? Alright. So the first one gives you about 76. Second one gives you about 799. And again, we're just learning the calculator stuff along the way. If we graphed it, that's what it would look like. With a window of 0 to 5 and 0 to 10,000. So you can see how it grows really quickly. And then here's another one. Cosmic ray bombardment of the atmosphere produces neutrons, which in turn react with nitrogen to produce radioactive carbon-14. Radioactive carbon-14 enters all living tissues through carbon dioxide, which is first absorbed by plants. As long as plant or animal is alive, carbon-14 is maintained at the organism level. And here's the formula: A equals A to the 0, E to the negative 0.000124 raised to the T, where A is the amount present. So we're going to use that equation. I'll show you in a minute. If we have 500 milligrams, how many milligrams would be present in the sample in 15,000 years? So there's your equation. And your job is to plug in 15,000. So, whichever way you want to do it, your equation is 500 e to the negative 0.000124 t. You're plugging in 15,000 in for t. So practice both ways. Use the table and type it in. Use the table and type it in. So this is practicing our calculator, knowing where the buttons are. Practice both. If you're great with the calculator, good. You're where you're supposed to be. If you're still struggling a bit, you're gonna have to practice. Okay, so one way is to put the equation in Y1. Be careful typing it in. Go to the table, delete the ones you have in there, type in 15,000, get about 77.8. Or, excuse me, thank you. We can just type it in. 500 e raised to the negative 0.000124 times 15,000, and you get the same answer. So it's just becoming comfortable with your calculator, comfortable with the keys, all that stuff. Any questions there? So we did about 77.84 milligrams. And if I wanted to find the half-life, let's first graph it. So I want you to graph it, and your window is going to be 0 to 50,000 is your x, counting by 10,000s. Your y is 0 to 500. So just get the graph first. Get the graph first. Look at the window, match the window, get the graph first. I'll remind you that the equation is 500e to the negative 0.000124x. Get that in first. The window is going to be 0 to 50,000, counting by 10,000s, and 0 to 500, counting by hundreds. So get the graph first. And my question is going to be, when is this equal to 250? So the life is 500, half-life is 250. When is this equal to 250? When is the equation equal? Not inputting 250. When is it equal to 250? So let's make sure you got the graph first. And a quick way to find when it's equal to 50, go to y equals. What are we going to make y to? 250. Hit graph, find where they intersect. All stuff we've done before, just making sure we remember. Okay, what do we push? What do we push? Second trace. Which one? 5. And what? Enter, enter, enter. We did this a lot last class. If you're forgetting what buttons to push, we got some problems. And the answer would be 5,590. Okay, so practice, practice. We did max, we did intersect, we did all that last time. Practice, practice, practice. So they're saying 6,000, but it's 5,590. Okay, here the calculator. Set up the window like we just did. Found where they intersect, 5,590. Questions there? Basically, just getting really comfortable with our calculator, getting comfortable with exponential, comfortable with all these different things. So the solution to the equation is rounded to 5,590. This gives us a better estimate of the half. Now, exponential regression. Because we did linear, quadratic, cubic, exponential is just another one. So I'm going to give you some time to see if you can do this on your own. Okay? So, let me set this up for you. The table gives the number of individuals in billions worldwide who could access the internet from home for selected years since 2000. So I'm going to write down the numbers for you. So our X and our Y. X is the year. So we're going to put 0, 4, 8, 12, 16. So 2000, 2004, 2008, 2012, 16. Our Y is how many users in billions. And it used to be 0.41 billion, then it was 0.91 billion, then it was 1.58 billion people using the internet at home, and that's 2.02 billion. In 2016, 3.42 billion individuals access the internet at home. Okay? So now, we're going to use list 3 and list 4. What I would like is you to get the data first. So you got to figure out the window, sketch the data, get the dots, and then you're going to do exponential regression. So you got to find that in the calculator. So when you're done, you should have the dots in your calculator and the line that goes through it from exponential regression. It's the same as linear, same as quadratic, same as exponential, same as algebraic. Now we're just doing exponential. So that's your little test for right now. Let's see if we can do it on our own. I'm going to walk around if I need something. No. Paper, window, all that are rules. You're doing what it's doing. I'm doing 3 and 4. Yeah, just because I do it, you follow along doesn't mean you can do it. You got to do it on your own. I'm great at this stuff. So I'm putting the data in 3 and 4 this time, not 1 and 2. Again, we're stopping, we're working together. Get the dots and line of those. So you see the dots and the line that goes through it, exponential regression. Give it a try. I'll go over it, you can follow along, you can copy it, you can do it on your page. Exponential regression. Just give you a hint. Exponential is 0 on calculator. Exponential is 0 in the calculator. Exponential regression is 0 in the calculator. Okay, a couple more minutes. Just try it on your own, because again, when you follow along, it's like, I can do this, I know how to do it. Try to find out later. where we're at. Because again, doing it with it is totally different than doing it on your own. Number one, if it was me, the very first thing I would do is understand the problem. I would put year on my axis. What year am I going to start with? 0. What will I go to? Probably 20. Count by 4. It's got already a natural 4 to it. I would do that first. And then my users on my y-axis, what would I probably start with? 0. And what would you count by and go up to? 4. Probably go up to 4 and count by probably halves. That's what I would do. So I'm going to go 0.5, 1.5, 2.5, 3.5. So to be honest, I could do the first part without the calculator. 0.41, 4.91, 8, 1.58, 12, 2.02, 16, 3.42. Okay, I can do that first part without the calculator at all. Okay, I can have my dots and not even touch my calculator, but understand what's going on. Okay, but I also want to do the calculator. So what do? I'm using 3 and 4. Some of you guys want to always use 1 and 2. You can do what you like. But I'm going to ask you that the very first thing you do every single time is go to y equals, get rid of that old stuff, and nothing in plot 1, plot 2, plot 3. All those should be unhighlighted when you start. It will be highlighted later. Then, how do I put the data in my calculator? What do I push? Stat, number 1 for edit. Now, I'm going to put my data in 3 and 4. Okay, I'm going to put my data in 3 and 4. So I'm going to clear list 3, clear list 4. If you want to use 1 and 2, that's no problem. Just always refer to 1 and 2. I'm going to use different lists. So 0, 4, 8, 12, 16, 0.41, 0.91, 1.58, 2.02, 3.42. Okay? And be careful. If one number is wrong, the whole thing's wrong. Now again, my expectations are higher. We did linear, we did quadratic, we did cubic. It's the 4th regression. If you don't know where to put the data in, you got a lot of homework to do. Okay? And you've been staring at me the whole time. You got to do it. Now, how do I see the dots? What do I push? Second y equals. Go into plot 1. Turn plot 1 on. Choose scatter plot. For me, my x is list 3, second 3. My y is list 4, second 4. I'm not going to do zoom 9. I'm going to make my own window, which I already did. So let's make sure we're all caught up. Everybody has the data in the calculator, and everybody set up their plot. Everybody with me? Then hit window. I'm going from 0 to 20, counting by 4s. 0 to 4, counting by 0.5s. And again, the window's right here. There's no magic to how I got the window. You could use zoom 9. It's just not my favorite. I prefer you not use it. Then hit graph. Let's make sure we all got the dots. Now, looking at the dots, why are we doing exponential? You see that little curve that it's taking? That looks exponential. I'll tell you which one to use. You don't have to guess. But in real life, you would try all the different ones, see which R² is the best, which one looks the best. Okay? Does everybody have the dots in their calculator? Okay? Now, exponential regression. How do we do all the regression? What do I push? Stat to the right for calculating. I didn't tell you what number it was until I gave you the hint. But number 4 is linear. 5, quadratic. 6, cubic. They're all here. We're looking for exponential. And where is exponential? 0. Choose 0. For me, x is list 3, y is list 4. If you needed 1 and 2, put 1 and 2, no problem. If you have the calculator blinking, make sure it's list 3, comma, list 4. but everybody should have the same numbers. Everyone should have the same numbers. Looking at your r squared and r, is it a good fit or not? Really good, because it's close to 1. And I'm going to put my number a in for a, b in for b, raised to the x. How many decimal places? The more the better. I'm going to use 3, but the more the better. If you did 4, even better. So I'm going to do users in terms of x, 0.483 times 1.134 raised to the x. It's exponential raised to the x. And all I did is put a in for a, b in for b. In your homework and stuff, if it says 4 decimal places, go 4. If it says 2, go 2. If it doesn't, 3 or 4 is fine. To make sure I'm right, go to y equals 0.483 times 1.134 raised to the x. And when I hit graph, what should that line do? Go right through the x. And again, it's not hitting all perfect, but it is pretty good fit. Question? Anybody need help? It's not working out? Calculator exploded? Brain exploded? Okay? All right. Now I'm going to add a question to this. You're going back, you put the data in the calculator, you did the dots, you did the regression, you got the line. Now the question wants to know when use the regression to estimate the number of internet users in 2024. So this question wants to know at 24, what will the number of users be? At 24, what will the number of users be? See if you can figure that out. Whichever method you want. You can use a table, you can just type it, whatever you'd like to do, but estimate how many internet users at 24. Which represents 2024. I would use a table if I were you, but it's up to you. Table's probably the easiest way. Okay. So if I go to the table feature, second graph, type in 24, what are we expecting for 24? 9.88. If you plug it in, they got 9.95, but look how many decimal places they rounded to. That's the difference. It's not that we did it wrong. They did 4 decimal places, which changes the answer. Okay, now before we move on, let me add one more question. I want to know what year will we have 3? What year will we have 3? So what year will we have 3? So not X, Y. When Y is 3, what year will that happen? See if we can figure that out. Not with the table. What do you think it is? 14.5 is one person's guess. You agree? So in this case, I'm not plugging in X, I'm plugging in Y. So how do I do this one? Go to Y equals, when will this thing be 3? Hit graph. Where's the answer? Second, trace, 5, enter, 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 at about 14.52. Okay? All this stuff you can totally do and use and help you with your homework and all that stuff. I'm just trying to help you along. Okay? All right. So, what else can we do exponentials for? Compound interest. So, P is the present value, R is the rate, A is the future value. And this will tell us if interest is compounded. Let me just explain how this formula works. A is how much is in your account. P is your principal, what you're starting with. R is the rate that you're getting. Excuse me, M is how many times a year. So if I said this is monthly, what would M be? 12, right? M is how many times a year, and then T is time. So, again, I know we're getting close to our limits. Let's go through this. If you put $10,000 in the bank, and you get a 7.5 annual rate, which nobody's going to give you, with interest compounded monthly, nobody's going to give you that. How much money will you have in the account at the end of 20 years? Well, P is 10,000, R is 0.075, M is 12, and T is 20. If I plug everything into that, that's what it would look like. So I want you to practice. Just type in this, and if you get it correctly, you should get this. So just calculator practice. Just type it in and make sure you get 44,608.17 cents. This is just, I know you can plug in the formula. I'm not worried about that part, but I am a little worried about your calculator skills. So type that in. Make sure you get 44,608. Sometimes it's the parentheses, sometimes it's dividing, whatever it is. Let's just make sure we're comfortable. So we're just typing it in, no calculator stuff. As far as graphing, just typing it in. This is compound. Let's get very comfortable with our calculator. An example of exponential. So if I typed in 10,000, 1 plus 0.075 divided by 12, close parentheses, raised 12 times 20. And again, if your calculator doesn't do the little raised part, just make sure 12 times 20 is in parentheses. That's the little stuff I'm talking about. Make sure you get 44,608.17 cents. Anybody not getting it? No? Again, get to know your calculator. This was the original. Questions there? Everybody getting it? Okay. Now, if your interest is compounded at a different rate, let's say it's compounded exponentially or continuously, then we have a new formula. That formula is A equals P e to the RT. A is your account, P is your principal, P is that number we used before, R is your rate, T is your time. So now, let's say we're using compounded continuously, 10,000 e to the 0.075 times 20. Type that into your calculator, see if you get that number. And again, I'm just practicing the calculator. I'm confident if you have the formula and you have the numbers, you can plug them in. I'm just going to practice the calculator stuff. Yeah, well, one is going to be missing. So let's say they give you A and R and T, you got to find P. So something will be missing and something that you'll have everything else. So this would be 10,000 E to the 0.075 0.075 times 20, 44,860. Okay? And that ends 1.5.